Okay, so you know that the volume of a sphere is given by 4/3 pi r cubed. We're going to use calculus to prove that this is true. And so, I've drawn spheres in two different ways here, just to show you, right, that a sphere consists of circles of different radiuses stacked on one another. So this is the main circle going through the equator, right? And then this is in another orientation, there's circles also that way. And so what we're going to do is I've set up a coordinate system where we have our circle, and we're going to be adding up circles that are in sort of this direction being stacked in the y. And they're going to, of course, have smaller and smaller radii until they get to 0. And so our volume then, we're going to call this point here is going to be point 0, comma r, right? It has a y value of r, the radius of the sphere, and the origin's at the center here. So our volume is simply going to be 2 times, we're going to be doing one hemisphere for our integral. So for 2 hemispheres, we need a 2 times the integral of 0 from r. We're going to be summing up these circles from 0 to r along our y, right? And then what is each one of those circles? What's the area of a circle? Well, the area of a circle is pi r squared, right? So it's pi r squared for one circle. But what is the r value? The r value is actually, if we're setting it up like this, it's going to be the x value of this circle. Okay, so up here it's going to be 0 radius. Up here it's going to be whatever the radius is, x. And so we need to know the formula for a circle, which is x squared plus y squared equals r squared. We can very simply solve for x then, and x is going to be equal to the square root of r squared minus y squared, okay? And so basically that means that all of our different circles, they're going to have a radius of pi times, they're going to have a radius of r squared minus y squared, the square root of that. So the area is going to be simply pi that squared, okay? And so, in other words, just to be explicit, we have pi times x squared and dy times by dy. That's going to be the volume. Essentially, we're looking at a sort of circle, perspective drawing being flat, and it has some height. The height, essentially, we're looking at an infinitesimally small cylinder, and the height is infinitesimally small, so we use the differential as dy. But the area there is pi x squared, right? Because x is the radius. So if we sum all those up with the integral, that's going to get us our volume of the sphere. So now let's just plug in what we already calculated. X squared would be, I put the pi out of the integral because it's a constant. And so we're going to have r squared minus y squared dy. And at this point, it just becomes simplifying this expression. So we're going to split that up into 2 integrals because we're subtracting integrals, and we're allowed to do that. So let's do that. It's going to be 0 to r squared dy, and then minus another one. We'll carry through the 2 pi here. 0 to r of y squared dy. And so now we can go ahead and evaluate these integrals. Well, this is just a constant, so the integral of r squared, which is constant, is just going to be r squared y, r squared dy. Okay. And then minus our next one, the integral of y squared is 1/3 y cubed, right? Because if you take the derivative of that and you do the power rule, and you bring down that 3, you get 3y squared times 1/3, that'll get you your y squared back. So now we can go ahead and plug in our values of our bounds here, r and 0. So we're going to get 2 pi times r cubed minus r squared times 0. And then we're going to get that minus 2 pi times 1/3 r cubed minus 1/3 0 cubed. At this point, we can see we have some terms with 0. That term's going to go away, and that term's going to go away. I'm going to end up with 2 pi r cubed minus 2/3 pi r cubed. Well, 2 pi is the same as 6 pi over 3. So 6/3 pi minus 2/3 pi gets you, lo and behold, 4/3 pi r cubed. And so that is your proof using calculus of how to calculate the volume of a sphere by adding up a bunch of circles.